according to the cloud. So again, page 49, number 3, we have cotangent times cosine plus sine is equal to cosecant. All right, so whenever I tackle a problem like this, I always look at it, again, with an impenetrable barrier, but I look at it with this idea in mind that, yeah, they have cotangents and cosecants, but I'd prefer to only have sines and cosines. So anywhere, once I decide which side I'm going to start on, I'm going to start on the left because that's the more complicated side. Anywhere I see something other than a sine or cosine, I'm going to make it a sine or cosine. Cotangent, by definition, is cosine of x divided by sine of x. All right. So then everything else is just going to come along for the ride. So I'm going to have cosine x plus sine x. This is a product. So I can put it together, right? That cosine could be thought of as cosine over a 1. When you multiply two fractions together, you multiply the top by the top and the bottom by the bottom. All right. So extreme close-up. These two get multiplied, these two get multiplied. So we're going to get cosine squared of x over sine of x. Plus the sine of x that's already there. Now, when you're adding two fractions, we want to get a common denominator. Right? Now, it's not obvious that they're fractions just yet until I put that sine of x over a 1. Right? So far, the only thing that we've done that's specific to trigonometry is this transformation, or this substitution, really. I don't want to get too fancy. Everything else so far has been algebra. All right, so I'm going to get a common denominator here, and I'm going to do that by multiplying the top and bottom by the sine of x. Top times top, bottom times bottom. So this will become sine squared of x over sine of x. Everything else comes along for the ride. All right. So now that I have my common denominator, I can put these together into one fraction, all right, over that common denominator. So on the top, I'm going to have the cosine of x plus the sine of x. Sorry, cosine squared of x plus sine squared of x. All right. Now that happens to be a rule. All right. So this is what we were talking about last time. You know, we talked about a lot last time, but among the things that we discussed was the Pythagorean identities. And that is that cosine squared x plus sine squared x by definition is equal to 1. So an equal sign with three bars means equals by definition. I mean, you could just write regular equal sign, but this is really the proper way of writing it to indicate that we didn't do any computations here. We're just applying a rule. That's equal to 1. And so this becomes 1 over the sine of x. And 1 over sine of x is equal to cosecant of x, which happens to be what we're looking for. Okay. So a lot of algebra and a little bit of trig. But the rules that we needed to know here, and actually I can just jot these down. The rules that we needed were that cotangent of x was equal to cosine of x over sine of x, and that cosine squared x plus sine squared x was equal to 1. Oh, and also 1 over sine x is equal to cosecant x, or vice versa. All right, so 3 trig rules came into play here, but it was really the algebra that made everything work. All right, so we'll do number 5 now, because number 4 we already did that anyway. But for number 5, you see it's just kind of a similar sort of look to number 4. The exception being there's just more stuff going on, but it's actually kind of nicer. You'll see in a second. So impenetrable barrier. We know cosecant is equal to 1 over sine. Maybe you don't have that memorized, but I wrote it right here. So it's not unfair to say that. We definitely know that that's true. All right, so 1 over sine of x. We know that cotangent is cosine over sine. All right, so we're looking at something that's got kind of a similar feel, right? But this one's going to work out in a more concise way, right? Because that cosine of x can be thought of as cosine x over 1. When you multiply, you get 1 over sine x minus cosine squared x over sine x. With that common denominator, I can say over the sine of x, we have a 1 minus cosine squared. All right. And we learned last time that this, by rule, is equal to sine squared of x. So we're looking at sine squared of x over sine of x. That simplifies down to just the sine of x. All right, and that's because sine squared of x is really the same as saying sine x times sine x. All right, so one of those sine x's will cancel away. All right. So then number 6, 1 over sine squared plus 1 over cosine squared somehow is going to be equal to 1 over sine squared theta cosine squared theta. All right, so impenetrable barrier. If I'm going to add these two fractions, I'm going to do it by getting a common denominator. All right, so I'm going to multiply top and bottom of my first fraction by cosine squared theta. All right, so it's kind of hard to tuck it in here, but if you write small, you can get it in there, but I'm going to rewrite. So top and bottom of the first fraction gets multiplied by cosine squared theta. Top and bottom of the second fraction gets multiplied by sine squared theta. So when you put it all together, we have our common denominator, sine squared theta, cosine squared theta, or the other way around. It doesn't matter because it's commutative. But on the top, I'm looking at the result of taking cosine squared, multiplying it by 1, which is cosine squared. Then adding to that sine squared multiplied by 1, which is sine squared. And we reviewed earlier that cosine squared plus sine squared is equal to 1, regardless of the variable. In this case, we're using a theta rather than an x, but it's still the same principle. So this piece here, by definition, is equal to 1. And so therefore, we're there. We have it. 1 over sine squared theta cosine squared theta is equal to, that's what's on the other side. So we're good. We got our proof. So one trig rule, but a fair amount of algebra. And it's really going to play out that way pretty substantially when you think about it. It's like every problem that we've done, a little bit of trig, a whole lot of algebra. For some people, that's music to their ears because maybe they don't like trig. But other folks are like, oh, dang it, I don't like algebra. I'm starting to enjoy this trig stuff. Well, we're going to get bogged down with the algebra. Yeah, it happens. But you start, when you get experience, you start realizing little shortcuts through the maze. Okay. Number 7 is probably the most intimidating looking one, but it's actually, believe it or not, the easiest one. Impenetrable barrier. But the thing is, if you don't have any experience with something like this, then it's pretty dang intimidating, right? So it goes back to factoring skills. And one of those skills involves a difference of perfect squares, or DPS for short. Some people call it that, right? But difference of perfect squares. All right, so the rule for that is if you have some expression a squared minus b squared, the factors are a minus ba plus b. All right. But honestly, I mean, when I learned difference of perfect squares, I didn't learn it that way. And I don't think of it that way, but in my experience, people just, they want the rule. So here's the rule. But what I look at when I see an expression that contains two terms connected with a minus sign is whether or not those two terms are perfect squares. If they're perfect squares, then we could use this approach. And so what we do is we take the square root of each part, make two binomials out of it. One has a minus sign, the other has a plus sign. So that's what's going to happen here. They're both perfect squares. If you're raised to an even power, you're a perfect square, right? Any even power, doesn't matter, right? To find the square root of a number that's raised to an even power, you just divide the power by 2, right? In this case, it's really not that complicated because you're talking about a 4. I mean, even if you accidentally took the square root of the 4, you'd still get the same number, you know? So, two binomials. The first entry in each binomial is going to be the square root of the first term of the given binomial. All right. So the square root of sine to the 4th would be sine squared. that goes here, sine squared theta, sine squared theta. Then we take the square root of the second term, that occupies the second position within the binomial. Square root of cosine to the fourth is going to be cosine squared. So cosine squared theta, cosine squared theta. One gets a minus, the other gets a plus. At first glance, you might look at this and say, okay, now what? You know, you get all jammed up. It's really not that bad, because even if you had to fake your way through this by just guessing, you're probably going to guess right, because if the left-hand side needs to simplify down to this expression, then this piece here would have to cancel away, because we need to be only left with this, right? Because this is still here, there must be a rule that we could apply to get that to cancel away. That canceling away must mean that it turns into a 1 somehow, right? So even if you didn't know, you could just kind of fake it and say, well, by definition, it's equal to 1. Why? Because it has to be, right? However, that's a Pythagorean identity, so it's equal to 1 anyway, right? So we have, after really one real step, we have our proof. And again, you've met the objective once you get the left side to equal the right side. So mission accomplished. All right. And you see here that, you know, we're 7 examples in, and I've been exclusively working with just the left-hand side. That's just a coincidence, really. You know, sometimes it's the right-hand side that's more complicated. It's just these particular examples have the left side being more complicated than the part, you know, that gives us the part that can be simplified. Gives us something to work with is really what I'm getting at. And the same deal for number 8. Impenetrable barrier. Tangent, by definition, is sine over cosine, so sine of theta over cosine theta. Cotangent is cosine theta over sine theta. If I want to add 2 fractions, I got to get a common denominator. So that means my first fraction, top and bottom, is going to get multiplied by sine of theta. Second fraction, top and bottom, getting multiplied by cosine theta. So we now have a common denominator of sine theta cosine theta. On the top, I'm going to multiply sine by sine. Gives me a sine squared. Plus, then I'm going to multiply cosine by cosine, so cosine squared. And this, by definition, since our Pythagorean identity, is equal to 1. All right. Now, this simplifies down to 1 over sine theta cosine theta. Now, there is a way to get from here to here. But what I'm going to do is I'm going to shift gears and say, you know what, maybe it's easier to just work the right-hand side. Because I know cosecant, as long as you work the 2 sides independently of one another, you know, don't bring anything from one side to the other, then you're in good shape. You're not breaking any rules. Cosecant is 1 over sine of theta. Secant is 1 over cosine theta, which when multiplied gives you the thing that you're looking for, which is 1 over sine theta cosine theta. And again, the whole point of this whole exercise is to get the left side equal to the right side to prove that these relationships are valid. As long as left equals right and you didn't break any rules along the way, you're in good shape. Alternatively, what we could have done would have been to break up this into 1 over sine theta times 1 over cosine theta, which in turn would have become cosecant theta times secant theta. So we would have got it either way. It's just a question of preference, really, more than anything else. So then we did number 9 together, where we did some variation of number 9 together. The number 10, good looking problem right there. I'm just going to shrink down this algebraic rule here. Just so I have some space. All right, so for number 10, again, I mean, it's pretty clear in this case that the left side is more complicated. I mean, you don't even have to know anything about trigonometry to say there's more stuff going on the left side than there is on the right side. All right, it's more complicated. That's where we should focus our attention. So I want to get a common denominator in order to add the two fractions. So I'm going to rewrite. Again, if you could sneak it all in there, that's fine, but I'm going to rewrite. All right, top and bottom of the first fraction gets multiplied by 1 plus sine x. Top and bottom of the second fraction gets multiplied by cosine of x. I went the parentheses route here to show the multiplication, only because we have some binomials and I don't want to make a mistake with that. Right, so I'm just being a little bit more careful. But we do have our common denominator. Now we could distribute out that common denominator. I don't know that I want to yet, though. I want to see how the numerator shakes out. So the common denominator, I can write it as 1 plus sine x times cosine x, or I could write it, the way I just wrote it, cosine x times 1 plus sine x. I prefer to have the single termed expression precede any multi-termed expressions. Just a preference. Right? But distributive property, we have to double distribute this binomial against this one. So, the old FOIL method, first, then the outers. So 1 plus sine x, then my inners, and then the last values. All right, so sine x times 1 is sine x, and then plus sine squared x. We need more fraction here. And then when I multiply cosine by cosine, that part's easy enough. That's cosine squared. Good. So then we take a closer look at what we have here. You might notice that hidden in this big old mess here is a trig rule. We have sine squared x plus cosine squared x. It's not a standalone expression, but it doesn't have to be. Right? Sine squared x plus cosine squared x by definition is equal to 1. So now I have this 1 here that could be added to this 1. And without really doing much of anything in terms of trig, it's been all algebra. we're able to simplify this down kind of nicely, right? Because I have 2 plus, now I have 1 sine x here and another 1 sine x there. So 2 plus 2 sine x. And believe it or not, we're in the home stretch. We have a common 2 that can be factored out right here. I'm going to pull out that 2, and that's going to give you a 1 plus sine x. And it's one of those situations where it's a, you know, I don't want to fake anything here and say, well, it's a good thing I didn't distribute out the bottom. I mean, I've done this problem enough times to know, like where the story goes. What I can tell you is I never distribute out the denominator of a fraction. When I get a common denominator, I always look to simplify the numerator, do some factoring there, because the denominator usually is already in factored form. And if you leave it alone, any common factors will be present within your denominator. Right, so we're in pretty good shape here because I have a 1 plus sine x that cancels away, leaving me with just 2 over cosine of x, which is the same as 2 times the secant of x, which happens to be what the other side was asking for. Check mark. All right. So yeah, this one had a little bit of oomph to it, but the oomph was the algebra. There was 2 little baby trig steps in there that were not difficult. All right. In fact, any instance that involved trig helped to make our algebra easier. All right. The last one that I'd say the last one doesn't really count because I was just getting this to the final step. But can you imagine if that sine squared x plus cosine squared x didn't cancel to a 1? It didn't simplify to a 1? Like, what would we have done? It would have all fallen apart. All right. But because it did, this worked out beautifully. So now we're going to spice it up. You're like, it's already spicy. We're gonna incorporate some indifference identities. I can't remember. Are we doing? I don't think we're doing half angle identities. Oh, well, I didn't say that we're doing half angle identities, so that's good. All right. Although, let me just check something real quick. Yeah. We will do half angle on the next page, but for now, it's just sum and difference identities. So we and double angles. So we go back to this neck of the woods, and what we have here are functions of the sum of 2 angles, functions of the difference of 2 angles, and functions of the double angle. A lot of rules. A lot of rules. However, you really only need to know like 5 of them. Now you're like, oh, 5 rules. Oh, how nice of you. Well, 5 as opposed to like the 11 that's, what do we have here? Is it 11? Yeah, about 11 rules. It's half of the rules that you see here. All right. And I'll show you some nicer ways to represent these formulas. First off, since tangent is equal to sine divided by cosine, any rule that involves tangent, yeah, it's nice to know it. If you have, if you have time and you like memorizing stuff, go ahead and add that to the list. But the bottom line is you don't really need to worry about memorizing rules that involve anything other than sine and cosine because you could always just figure those out. All right. Eventually, you want to get to a point where you're proficient with that, but at least in the early going, not as necessary. Right. So we only need sine, cosine for the sum, difference, and double angle identities. All right. You'll see that there are 3 different variations of the cosine double angle identity. All right. Well, these 2 are based off of a substitution related to this one. So if you know the first one, you could figure out the other 2. All right. So that kind of streamlines things even more. Now, what I like to do because if we notice that the structure for the sine sum rule and the sine difference rule is pretty much the same, except one has a minus and the other has a plus, we can streamline these two rules down to really one rule. And that would be the sine of A plus or minus B is equal to the sine of A times the cosine of B plus or minus cosine of A sine of B. All right, so basically just kind of smushing them together, because the plus in this rule here would correspond to the plus in the expansion. The minus in the left side of the expression would correspond to the minus in the expansion. All right. We could also do something similar, but for cosine. So these two rules, you'll notice that the sum rule has a minus sign in it. And the minus rule or the difference rule has a plus in it. All right, so the way we would write that, the shorthand way of writing it, would be to say that the cosine of A plus or minus B would be equal to the cosine of A times the cosine of B minus, on top of the plus, sine A sine B. Meaning the cosines, I'm sorry, the plus corresponds with the minus and the minus corresponds with the plus. All right, so we're able to take four rules and make them into two rules, two unique rules. All right, so out of all of this stuff here, all of this information here, we have these two modified rules that we just created, and then these two guys. This one and this one. All right. So let me just talk to you a little bit about the cosine double angle. Cosine 2A is equal to cosine squared A minus sine squared A. All right. Now, we know, because we talked about this, but you know, like it's the kind of thing, like, I mean, we don't all have instant recall. So we know, as in like we wrote it down somewhere. It's been taught. Maybe you don't remember it quite yet, but you will if you work at it. Cosine, I'm going to write it up here. Cosine squared A is equal to 1 minus sine squared A. All right, that comes from the Pythagorean identity, the first Pythagorean identity. And sine squared of A is equal to 1 minus cosine squared of A. All right, the reason why that's important is because if I replace cosine squared with 1 minus sine squared, I get a new rule, which would be 1 minus 2 times the sine squared of A, which is this one. So basically what I'm saying is you don't really have to know this rule, because you can always figure it out just by making a timely substitution. All right. The other thing that we could do is replace the sine squared with a 1 minus cosine squared. So that would give us cosine squared minus 1 plus, distribute the negative, another cosine squared. So we'd have two of those cosine squares. and that would give us this other rule. So really, it's just working off, like I said, it's just working off of 4 unique rules. Right? But it gets a little overwhelming because that's added on to the rules that we already are responsible for from last class. Right? Yeah, and you could look these up. That's not a problem. It's just knowing enough to know that it's a situation where you need to look up a rule. That's the thing. It's the difference between memorizing and being familiar with, right? So what's happened in the past, and this happens more in my high school classes, but it also happens in the college classes too. It might be a maturity thing. I don't know. But what'll happen is the crutch of being able to look up rules kind of becomes a little bit of a setback for students, because what happens is they get to the point where they're constantly looking up rules and they never internalize them, and because of that, when they get into calculus, they just don't know the rules, right? As opposed to the students who at least make the attempt to try to remember the rules, at which point, yeah, maybe you don't remember them, but you develop a little bit of a familiarity with the formulas, the rules, so that when you come across it in a problem, you say to yourself, this is a rule. I don't know what it is, but it's a rule. At least you know enough to know that it's something that you have to look up, right? And so that's really the moral of the story here, right? So I'm going to snag really just these two to get started, because I'm gonna bring these over to that other page with the identities. And identities are kind of, I mean, they're interesting, I think, but they also they serve a purpose other than just being fun math puzzles. The term fun is relative, I guess, but it kind of it forces you to apply the rules, the sum difference identities, the Pythagorean identities, and all that stuff. So you kind of get into a habit of looking for a formula to make a timely substitution. It goes a long way. And also you're kind of setting yourself up nicely to be able to handle more complicated trigonometric expressions that you look at it and say, well, there's got to be a simpler way to write this. Maybe there's a rule that I can apply. All right. So this first piece here, again, impenetrable barrier. Sine of x plus y. Well, we have an a quote unquote a value and a b value. All right. This sine of x plus y would follow, I'm sorry, x minus y would follow the purple variant of the sine rule. All right. So this would become sine of x cosine of y minus cosine of x sine of y. Right? All because of the presence of that minus sign. This one follows the yellow variant, right? And that's the plus. So I'm just running through this expansion here. Just everywhere I see an a, I'm replacing it with an x, my a value. Everywhere I see a y, a b, I'm replacing it with a y. So I'm looking at sine x cosine y plus cosine x sine y. And believe it or not, we're pretty much done. I mean, there's only like a step and a half left, because these two here, really got to time my highlighting. these two here are exact opposites of one another. It's commutative. So this is the same as saying negative sine. Time out. Sorry, highlighted the wrong thing. Apologies, everyone. These two are exact opposites of one another. So they would cancel each other out. In which case I'd be left with 1 sine x cosine y plus another 1 sine x cosine y. Two like terms, put them together, I'd have 2 sine x cosine y. All right, so this is the first departure from what we were doing on the previous page, in that the rule was the determining factor, defining factor in being able to get to our solution here, right? Whereas there, you know, like every other problem was like a little bit of trig and a whole lot of algebra. This one had like as minimal amount of a minimum amount of algebra that's possible, but it was completely defined based off of the trig rule, right? So that was kind of different, right? And it's going to be the same way anytime you see some argument within a trig function other than just an x. All right. So, and what I mean by an argument is sine of x, the argument is x. Sine of x minus y, the argument is x minus y. So whatever's contained within the trig function, if it's more than just an x, you're going to involve, so there's got to be a trig rule for it, right? So for the second example, we would have cosine of x minus y, right? Again, it's the same situation where we have an a and a b. You know, while I'm here, there we go. Any more of them? Yeah, I got one down here. So the a value and the b value are being subtracted. So I'm looking at the purple variant of the cosine relationship, right? So cosine a minus cosine b is going to be cosine a cosine b plus sine a sine b. All right. Again, it's not a mistake, not a typo. That's just how the rule works. It's so weird. Yeah. But there's actually a good justification for it. It's just we're not there yet. Right. Now, I can, if I want, I can switch over and start working the right-hand side, because I can make cotangent into cosine over sine. I can make tangent into sine over cosine. I can go that route. But I can also split this fraction. I can split it by the plus sign and make this cosine x cosine y over sine x cosine y. And it's kind of tricky to understand why this would be the way to go, but it really kind of boils down to the idea that you want to undo what was already done. All right. In most cases, like on the previous page, the previous couple of pages, you were given something that actually looked like the right-hand side of this expression, or this equation, right? Where you had to write it as cosine over sine plus sine over cosine, and then get a common denominator to put those two ratios together. But the left side here, the ratios were already put together. Somebody found a common denominator and combined the two fractions. So once I realized that that's what was done, I want to undo that. All right. If something's in factored form, I want to distribute it out. If something's distributed out, I want to factor it. If you're going to try to manipulate an expression, you need to be thinking about undoing what was already done. All right. So here I have a common cosine y. I have a common sine of x. Cosine of x divided by sine of x is equal to cotangent of x. Sine of y divided by cosine of y is equal to tangent of y. And so that's my proof, because that's what's on the right hand side. All right, number 3, there's a bunch of different ways to go about it. It really depends on the approach that you want to take. Like, because I just got through saying that you don't need to know the rules for tangent, secant, and all that other stuff, because if you know it in terms of sines and cosines, you could always figure out the other stuff. That being said, if you happen to know the rule for tangent, the double angle rule for tangent, this one's pretty dang easy. Right? As I can show you, you see we have a common 2 on the bottom of the left-hand side. So I can factor out a 2. And that would give me 1 minus tangent squared x. That 2 would go into the 4 twice. Now, at this point, maybe you're suspecting that there could be a rule in play. Okay, so you'd flip back a couple of pages, few pages, and you see here we have the tangent rule for the double angle. 2 tan A over 1 minus tan squared A. Actually, let me just bring that with me. So this is a rule, and you see it's the same thing, where we have the same thing written down, except we're using x's instead of a's. So that must mean that this is equivalent to the tangent of 2x. So that one's pretty easy. Now, alternatively, you can make each tangent into a sine over cosine, but then there's a pretty heavy amount of algebra involved. Right? So, that part is kind of a dealer's choice, I guess. Now, looking at number 4, you see we have the sine of 2x on the right-hand side, but the left-hand side actually looks more complicated. So I'm actually going to work that side. So sine x plus cosine x times sine x plus cosine x. Apply the distributive property. Okay, so a little FOIL method. First outer, inner, last. Oh, that's fun. So sine times sine is going to be sine squared. Sine times cosine is sine cosine. Cosine times sine is cosine sine. But that's the same as sine cosine. Doesn't matter what order you're in. I'm going to offset it below. And cosine times cosine is cosine squared. So this actually cleans up kind of nicely. First thing I notice is that I have sine squared plus cosine squared. Addition is commutative, so it doesn't matter what order I add these two things in. I can just pluck out the sine squared plus cosine squared. That's going to be equal to a 1. Then I have 2 of those sine x cosine x's, so plus 2 sine x cosine x. Now, you might look at this, this kind of, I don't know, it sort of speaks to what I was talking about before with number 1. Was it number 1? No, it wasn't number 1. It was a problem on the previous page. It was the top left problem on the previous page. The sine to the 4th minus cosine to the 4th, where you may not recognize a rule, but common sense tells you that it has to be a rule, because in order for the left side here to equal the right side, this must be equal to sine of 2x. That's the only way that this could work. And that happens to be the double angle rule for sine. All right. And if you're not sure, I mean, aside from referencing rules, you could also put it in Desmos and have a quick look. 2 sine x cosine x, you just graph that. All right. And then also graph the shorter version of it, which would be sine of 2x. See if they give the same graph. Same graph must be equivalent. All right. So the last 2 problems here, well, one of them, number 5, is kind of a rehash of something we already did, so I'm going to throw a star on that. And number 6 is kind of I'll call it a challenge problem, but I also, I don't want to rush into doing that one, so I'll let you have a little time to stew on that one, and we'll talk about that one next class. But I wanted to move on to numerical situations. Right, where it's not just the beautiful puzzle that is trig identities. We actually want to be able to apply these principles to numerical situations. Right. So on the next page, they ask us to find some trig functions. So cosine of 105, for example, and we have sine of 75 and tangent of 165. And those are not unit circle numbers, right? But we can use our knowledge of the unit circle to help us figure those out. All right. So sorry. I just want to, oh, no, it would be in another folder. I have a unit circle somewhere, and I wanted to just import it just so I can point to it. So let me input a blank page and get that unit circle in here. I'm trying to remember where I put it. I think it might be in my camera roll. The problem is a lot of things are in my camera roll. Super can. Oh, there we go. Oh, that's a blank one. All right. I'm going to do it the old-fashioned way. Fill in the unit circle. And let's see. It's under embedded math. The unit circle. Yeah, it's a good looking unit circle right there. Been using this for years. I think it left the page number. Yeah, I didn't want that. All right. Good looking unit circle. Right in the notes. Something to refer to. All right. Come back to that. We want to find something like the cosine of 105 degrees. I mean, we could conceivably put that into Desmos. Now it's a degree measure, so you got to be careful. When you put in something cosine 105, you know, a wrong answer and a right answer might look strangely similar, right? You just got to make sure you're in the right mode. In Desmos, you hit that little wrench, and on the bottom, you'll see radians or degrees. Right? So if you need to do it in degrees, just tap on degrees and kick out of there, and it'll give us the value in the appropriate form, right? So as opposed to radians. So you see, looking at the difference, it's not too far off, right? So you just got to be really careful. Now, regardless, we could actually come up with an exact value. So something in radical form. Yeah, and what I tend to do whenever I'm given a trig problem and I'm just feeling lazy and I don't want to do it in my head or I don't want to write out a solution, what I'll do is I'll just put it into my calculator. Like, for example, if the question's of sine of 45 degrees, you know it's going to be the square root of something. So what I do is I just square it, convert it over to fraction form, and then slap a radical over. Okay, so there's workarounds, but for something like this, that doesn't quite work, right? So what we need to do, I don't even know what I was about to do here. What we need to do is use a sum identity, well, a sum or difference identity, right? Because even though 105 is not one of our special angles, and when I say special angles, I mean in the unit circle, any one of these angles, as you work your way around, we call those special angles. I mean, I don't think I have a patent on that name. It's just they're the ones that give us nice answers in the unit circle, right? So any one of these angles would be preferred, right? So 105 is not one of these angles, but maybe it's the sum or difference of a couple of those angles. So for example, I can do something like cosine of, let's say, 60 plus 45. I'm just looking for two numbers, two special angles in the unit circle that can add together or subtract to give you that number. I mean, and this is just only one possible pairing. Yeah, I'm looking for 105. I mean, I could have taken 150 and subtracted from it 45. I would have got the job done. All right. So a lot of different possibilities. You just need one that works. Right. Now, the benefit of having it in this form is the rule cosine of A plus or minus B is equal to cosine of A, cosine of B, minus plus sine A, sine B. All right. So I want cosine of 60 plus 45. Right. So that's the yellow variant here. Right. So cosine 60, cosine 45 minus sine of 60, sine of 45. And at first glance, it's wow, out of the frying pan into the fire. We just made this so much worse. Well, not really, because we now have the ability to get an answer, a relatively clean answer, because these are all unit circle ratios. I could figure out each one of these based off of knowledge of the unit circle. Right. So if we go down here and look at our circle, the relevant angles are 60 and 45. Right. So at 60 and 45, let's see if I can, no, would have been nice. Oh, I didn't put image on. Right. Try that again, shall we? Yeah, that looks pretty decent. So at 60 and 45, we have some ratios. I'm going to bring this in here. I'll refer to it and then I'll shrink it down. All right. So remember, around the unit circle, the x value is cosine of the given angle and the y value is sine of the given angle. All right. So for cosine of 60, I'm just going to the 60-degree angle here and identifying the x value, which would be 1/2. For cosine of 45, I'm going to the 45-degree angle and identifying the x value, which is radical 2/2. For sine of 60, I'm just going to the y value at 60 degrees, which is radical 3/2. And for sine of 45, I'm just going for the y value at 45 degrees, which is radical 2/2. Multiply our fractions. And we get radical 2/4 minus radical 6/4, which is radical 2 minus radical 6 all over 4. Right? Now, when we put in cosine of 105 in degree mode in Desmos, we got this number. If we put in radical 2 minus radical 6/4, we get that same number. We get that same decimal. But the odds of you coming up with that ratio, that radical ratio from the decimal, very, very remote. Right? So that's really where it's at. Let's see. I can still use this for the next one. All right. So for sine of 75, again, we're looking for the sum or difference of values, angles, nice unit circle angles that would get us to a 75. 30, I mean, it's a little cut off, but 30 and 45 will get the job done. All right. So the sine sum difference identity, sine of A plus or minus B is equal to sine of A cosine of B plus or minus cosine A sine B. All right, so my expansion here, we're following the plus. The sine of 30 plus 45 is going to be sine of 30 cosine of 45 plus cosine of 30 sine of 45. So then it's just a matter of referencing the unit circle, at least until you get to the point where you have instant recall on it, which you'll want to have before calculus. Right, but sine of 30, the y value at the 30-degree angle, which is 1/2. Cosine of 45 is the x value at 45 degrees, radical 2/2. cosine of 30 is the x value at 30 degrees, radical 3 over 2. Sine of 45 is the y value at 45 degrees, which is radical 2 over 2. All right, so we're looking at radical 2 over 4 plus radical 6 over 4. And we'll say radical is the word of the day. So radical. Like totally radical, dude. Like that kind of radical. Or, you know, radical as in like mathematically radical. But we get radical 2 plus radical 6 over 4. I want to verify that because, you know, you do all this work. Why wouldn't you want to verify it? Because I don't like math. But yeah, I know. But you still want to make sure you got it right. It's kind of like, I don't know, and it is correct, but I kind of equate it to being in the dentist chair, you know, like you're going for root canal and, or you know, something major. You know, you're in the chair for like 3 hours, the dentist is going to town. And right when you're just about finished, he's like, you know, let me just have another quick look. And then he finds something that wasn't quite right. Part of you is like, why did you check? But then the other part of you is like, well, if he didn't check, then I'd be in pain when the Novocaine wore off and I realized that there was a mistake. Yeah, so I don't know. I don't know if it serves my purpose to equate my teaching with being in a dentist chair for a serious oral procedure, but that's the best thing. Sometimes I don't think I'm too far off base with that. So I'm just going to throw this in here. I think it's kind of nice. Anyway, the next one, sine over cosine, is what tangent is equivalent to. This is the one that I want you to jot down and submit for the check for attentiveness. All right. So this is the one you'll on it, you know, in your notes, on paper, whatever, you'll put your name somewhere, you know, maybe here. And then everything else that I put in this box here is what you're going to submit. Well, that didn't work out. All right, I think I just have to live with it, and that's just how it's going to be. All right, well, you get the idea. So anyway, 165, same idea as 105 and 75. It's got to be the sum of two values. All right, but before we even get into that, unless you want to go down the road of, well, I guess we're going to learn a new rule for tangent, we want to first think of tangent as sine over cosine. So sine of 165 degrees over cosine of 165. All right. Now we want to find the nice unit circle angle that's going to get us to 165, or a pair of angles, I should say. All right. So if I'm thinking addition, I could be saying something like, all right, well, something smaller than 165, like 135, for example. What would I add to 135? You know, like you just start with something and go from there. Right? If you can incorporate a quadrantal angle, that would be even nicer because those tend to clean up pretty well. Quadrantal as in the ones that are on the axes, like a 90. But 90 plus 75 will get you to 165. Now, if you get kind of cute with this, you can you can kind of build off of a previous answer because we know what the sine of 75 is now. So you could go that route, but that gets ugly very quickly. Right? So if we want an efficient way to get to 165, we're probably living in the second quadrant in some capacity. So I'm just going to pop this down over here. All right. Now I said 135. 135 and 30 will get the job done. You could do 120 and 45, but you could also think about maybe going a subtraction route. You know, think about ways in which you could subtract to a number. That's another possibility. Yeah.
Do you want us to draw the circle in the identity?
You don't have to draw the circle. Good question. You don't have to draw the circle. That's probably a little too much. Right. So sine, I'm going to go with, I said initially 135 and 30, so that's what I'll do. 135 plus 30 over cosine of 135 plus 30. All right. So we have two rules that are going to be in play here. We're going to have the sine double angle rule. I'm sorry, double angle. Sum and difference identity. So I'm just rewriting them again. And so are you. So sine of A plus or minus B is equal to sine A cosine B plus or minus cosine A sine B. And then we also have cosine A plus or minus B, which corresponds to cosine A cosine B minus plus sine A sine B. All right, and so what we're going to get out of this, again, sine of 135 plus 30 over cosine of 135 plus 30. The 135 is going to take on the role of the A value, and the 30 is going to take on the role of the B value. All right, so we're gonna pop it into the yellow variant, if you will. And so we'll be looking at sine 135 cosine 30 plus cosine 135 sine 30. Then on the bottom, cosine of 135 cosine 30 minus sine 135 sine 30. I'm just going to put these here for reference, but it should be pretty easy now because all you're doing is pulling values off of the unit circle. All right. So the 30-degree reference angle and the 135-degree reference angle, those are the only ones I care about, or we care about. All right, so this is my 30. So sine of 135 is the y value at 135 degrees, which would be radical 2 over 2. Cosine of 30 is the x value at 30 degrees, which is radical 3 over 2. Cosine of 135 is the x value at 135 degrees, which is negative radical 2 over 2. Sine of 30 is the y value at 30 degrees, which is 1/2. That's the top. The bottom, cosine 135 is the x value at 135 degrees, negative radical 2/2. Cosine of 30 is the x value at 30 degrees, radical 3/2. Sine of 135, the y value at 135 degrees, which is radical 2/2. And sine of 30 is the y value at 30 degrees, which is 1/2. So now we just got to simplify a little bit, but it's not going to really be too crazy. Because we're looking at radical 6/4 minus radical 2/4 over negative radical 6/4 minus radical 2/4. Which cleans up even further. And you could actually, I mean, there's a couple of steps you could skip along the way here, but I'm going to show them all anyway. Radical 6 minus radical 2/4, common denominator, over negative radical 6 minus radical 2, also over 4, which would be radical 6 minus radical 2 over negative radical 6 minus radical 2. And again, just like I said before, the whole dentist chair analogy, like you wouldn't do all this work and not check your answer. So tan is in tangent of 165 is that funky looking decimal. Let's see if this funky looking fraction gives the same funky looking decimal. Same funky looking decimal. All right. Now, somewhere along the line, somebody said that you're not allowed to have radicals in the bottom of a fraction. I think I mentioned this before. I don't know why that's a rule. I suspect it's because they wanted to make students learn how to rationalize denominators. And so they said, you know, you just can't have a radical in the bottom of a fraction, but that's not true at all. So we have a radical in the bottom of a fraction here, and it's perfectly fine. Like I said, you don't have to copy down the little unit circle snippets. I'm just putting it here for reference.
So whatever was in the first box, we need to copy down, right?
Yeah.
Okay. And on the bottom of the first fraction, that's a -6, right? Over
Correct.
4.
Negative
Okay.
radical 6.
Mm-hmm.
So just one more thing. And that has to do with what's known as a half angle identity. All right. And so the notes, you know, like those rules on a couple of pages prior, you know, like way back when, those are going to be really important. But what I'm going to ask you to do, and I'll come back to this in a second if you're still copying it. But what I'm going to ask you to do is just jot down this one relationship. This is not for submission, but it's pretty important. And so what I'll do is I'll actually just pull this, bring it down to the area below, so in case anybody's still copying, they can have access to it. So So I'll write it here, but then I'll move it back up to the other page in a few minutes. It's just I didn't want to leave this screen just yet, right? But what I wanted to show you, it's kind of interesting, I think. Right? So let's say, for example, we're looking at it really, I mean, there's a bunch of different variations of this, but let's say we're working with cosine of 2x, or 2a, sorry, is equal to 1 minus 2 sine squared a. Right. This is one of those things that, like, honestly, I'm never going to test you on it. That's what I'm about to show you. But it comes up enough in Calc 2, which is probably one of the furthest things from some of our minds at this point. It's like Calc 2, we haven't even done Calc 1 yet. But I always get, aggravated is not the right word. It's like when I start explaining this concept in Calc 2, as if my students have already seen stuff like this before, I'm always surprised at the fact that they just haven't, right? So I like to show it just so you're exposed to it, even though, you know, the chances of you remembering it between now and then are kind of slim. It's sort of worth talking about, especially for those of you who like to know where rules come from. It's kind of a cool relationship, right? So we have this rule, this double angle rule for cosine. And I just grabbed this one. It really doesn't matter which one. There's 3 variations of it, but here's a rule. What we can actually do is solve this rule for another part of the equation, right? It's solved for the cosine of 2a, but I can easily solve it for something else, right? And in this case, I want to solve for the sine of a.
Professor, is also in the submission or
No.
okay.
So I'm going to solve for the sine of a, and in doing so, I'm going to subtract the 1 from both sides. So I'll rewrite it again. So subtract the 1, and I get, and you know, I could write this a couple of different ways, but I'm going to write it as -1 plus cosine of 2a. That's equal to -2 sine squared a. Then I would divide both sides by a -2. And that would leave me with sine squared a is equal to, on the left-hand side, I got a -2 on the bottom. What I can do to handle that is factor out a -1 on the top. And simplify that -1 against the -2. And so what that gives me is a new ratio of 1 minus cosine 2a over 2 equal to the sine squared of a. Now, if I want to get just the sine of a, all I'd have to do is take the square root of both sides. So since I'm actively taking the square root of an equation, the power of 2 and the root would cancel on this side, leaving me with just a sine of a. But on the right-hand side, I'd have plus or minus the square root of 1 minus cosine 2a over 2. Now, what's happening here is we actually have the half angle identity. This is a function of a half angle. And so if you look at the rule here, you see that the structure is identical. Right? It's got the same exact structure. It's the sine of something equals plus or minus a radical 1 minus cosine of something over 2. Right? But if you look at the relationship here between the 1/2 a and the a, you see it's a 2-to-1 ratio. That's exactly the same as over here. I'm looking at a 2-to-1 ratio. All right. So what we end up doing here is dividing a by 2, and that gives us a new rule. And actually, let me put this back where it belongs.
Professor, are we supposed to be copying this down with what you're moving?
No,
No? Oh, goodness. Okay. All right. Thanks.
no problem. So what we do here is we divide a by 2. And what we would get is plus or minus the square root of 1 minus cosine of a over 2 is equal to the sine of 1/2 of a. And so that's a half angle identity, but it's still going hand in hand with what I was saying before, that you only need to know a certain amount of rules because you could always just kind of create the remaining ones. But this one would be kind of a stretch, like to be able to say, oh yeah, totally, I can invent this rule on the fly. It'd be super easy, barely inconvenient. Yeah, not really very practical, but it is doable. And the same process happens when you want to solve to identify the cosine half angle identity. Right? Except you would start with the rule where cosine of 2a is equal to 2 cosine squared a minus 1 and solve for cosine. That would give us this relationship. And then for tangent, you're just taking the sine relationship and dividing it by the cosine relationship. Okay, so there's always these algebraic processes that get us to where we want to go. So anyway, that kind of falls under the category of fun fact of the day. But it is stuff where, like if you want to go down the math road, you're going to have to know it at some point. It's a question of whether that's today. So that's where we're going to leave it for tonight. So if you came in late, check before you go. Otherwise, enjoy the remainder of the evening, and I'll see you all on Wednesday.